Hi folks, we're taking a look at the Chapter 2 review for Math 611B. I'm going to go through all the questions, some of them pretty quickly, but I don't think it's the best plan to just watch the video in its entirety. Skip to those questions that are stumping you. Alright, here we go. In number 1A, all you need to do is substitute in, and you're going to get 29. B is the same. You can substitute in, remember that e to the 0 is 1, and you're going to end up with an answer of 2. Alright, C, we've got lim as x goes to 1 of x squared plus 3x minus 4 all over x squared minus 3x plus 1. We want to factor this. So that'll give us x plus 4 by x minus 1. And I'm sorry, that was 2x squared on the bottom. And then a 2x minus 1. And an x minus 1 on the bottom. Okay, we work these out. Looks like we can divide out our x minus 1. And we get lim as x goes to 1 of x plus 4 all over 2x minus 1. Now we can substitute in, and that will give us 5. D is pretty similar. We want to look at factoring. Remember how we factor difference of cubes and difference of squares. So this is going to be lim as x goes to 1 of x minus 1 x squared plus 1 times x, which is 1, plus 1, all over x minus 1, x plus 1. Again, the x minus 1's divide out. That'll give us 3 on the top and 2 on the bottom. So we get 3 over 2. E, we've got some radicals. So for E, we would see lim as x goes to 3 of root x plus 1 minus 2 all over x minus 3. In these cases, we know to multiply by the conjugate. When you see radicals, this is typically going to be our TAC. That means on top we're going to have x plus 1, square roots are gone, minus 4, okay, which is just x minus 3. On the bottom, we're going to have x minus 3 by, in brackets, root x plus 1 plus 2. Again, notice the x minus 3 divides out, and now we can just put in a 3, which is going to give us root 4 here plus 2. We had a 1 on top. So root 4 is 2 plus 2 is 4 on the bottom, or 1 over 4. Okay. For F, we've got lim as x goes to 0 of sine 5x over x. This would be a whole lot better if we had a 5x on the bottom. So we can't divide out those x's. All we can do is build a 5x on the bottom. And if we times the bottom by 5, we need to multiply the top as well. Gives us lim as x goes to 0 of 5 sine 5x rather, over 5x. And this expression here, as x goes to 0, that's the number 1. So we're going to have 5 times 1, or 5. For letter G, we've got lim as x goes to 0 of sine x over 2x squared minus x. We look for opportunities to factor. That means the bottom is this. Sine x over x by 2x minus 1. Okay, obviously we can't substitute here, but I can split those fractions apart. That's a sine x over x times a 1 over 2x minus 1. And as x goes to 0, this expression right here is going to become 1. and this is going to become negative 1. Okay, so I'm not subtracting 1 from that. I'm just telling you what it's going to become. 1 times negative 1 or negative 1. H, lim as x goes to 0 of x plus sine x over x. Again, you could split these fractions apart. So you'd have x over x plus sine x over x. And each of those goes to 1. So we'll have 1 plus 1 or 2 for h. For I, lim as x goes to 0 of 3 over x plus 2 minus 3 over 2 all over x. We have nested fractions here, so we want to times by 2 by x plus 2. Let's see what happens. By 2 by x plus 2, so that's 3 times 2 is 6, minus 3 by x plus 2, so that's going to be negative 3x minus 6, all over x by 2 by x plus 2. Which gives us lim as x goes to 0 of negative 3x over x by 2 by x plus 2. X's divide out. And now that's going to be negative 3 on top. And the bottom will just be 2. I can substitute now. So 2 times 0 plus 2. Or 2 times 2, which is 4. Lastly, j. We have lim as n goes to 0 of 1 over n minus 1 over n squared plus n. Okay, two separate fractions here. I can't substitute, but I could try and put them together. So before putting them together, I need to find out what the common denominator is, which means factoring the bottom. That tells me the LCD is n by n plus 1, meaning I just need to multiply the first thing by n plus 1 over n plus 1, the first fraction. Lim as n goes to 0, that'll be n plus 1 minus 1 all over, now we have our common denominator, n by n plus 1. Clean up the top. Gives us n over n by n plus 1. Okay, these are gone. That's a 1 on top. And finally, I can put in 0 for n. So that will be 1 on the bottom and 1 on the top, or 1 in total. Okay, moving on to number 2. We've got lim as x goes to 0 of x to the 4th cos 2 over x. Obviously, we cannot substitute in 0 because that would be cos of undefined. And it's to show that question. So I've already given you the answer is 0. But we need to show that that's true. And the way we do that is with the squeeze theorem. So I'm going to say cos of 2 over x. It's going to be of whatever the angle was in the question. Lies between negative 1 and 1. Now, I need an x to the 4th out front. So I'm multiplying my cos of 2 over x by x to the 4th, which means multiplying each of the ends. I can evaluate these limits. So lim as x goes to 0 of negative x to the 4th is 0. Lim as x goes to 0 of x to the 4th is 0. And because of that, and the fact that this limit is squeezed in between them, this must also be 0. Pretty similar for number 4. We want to show that lim as x goes to infinity of sine x over x squared is 0. So let's start off with the fact that we're dealing with the sine x. That needs to lie between 1 and negative 1. I need to put it over x squared. So that means dividing each term in the inequality by x squared. And this one's talking about the limit as x goes to infinity. So those are the limits that I evaluate. As x goes to infinity, negative 1 over x squared becomes 0. Negative 1 over really big. As x goes to infinity, 1 over x squared. That also goes to 0. And that means that sine x over x squared is sandwiched in between them, and its limit must lie between 0 and 0, so it must also be 0. Okay, part B asks us to find this limit. Lim as x goes to infinity of 3x squared plus sine x all over x squared, which we could rewrite as the limit as x goes to infinity of 3x squared over x squared plus sine x over x squared. Okay, just splitting apart that fraction. Clearly, this first one is going to be 3. And this part right here, we just found it in part A. It's a 0. So that word hence, it means from here or using what you just found. Okay, number 5. Use a sketch. This is all dealing with the function y equals 1 over x minus 2, which we know looks like this. Okay, so just from looking at that graph, as we approach 2 from the right, we're going up to infinity. As we approach 2 from the left, we're going down to negative infinity. As we go out towards positive infinity, we're heading out to 0. And as we head to the left towards negative infinity, we're also heading towards 0. Moving on to number 6. A, the limit as x goes to infinity of 3x squared minus 1 over 2x squared plus x. Okay. We can do this formally. So if we do it formally, then we times the top and bottom by 1 over x squared. That's going to give us 3 minus 1 over x squared all over 2 plus 1 over x. Both this and this are going to 0 as we go to infinity. So you'll be left with 3 over 2. Or you can use the shortcut, which is highest power on top, highest power on bottom. And that'll give us 3 over 2. You use the shortcut when we've got a rational function, meaning a fractional function, and we're going out towards either infinity or negative infinity. All right, for B, we have lim as x goes to negative infinity of 5x plus 1 all over 3x squared minus 2. Okay. If we do the shortcut, that's lim as x goes to negative infinity of 5x over 3x squared, which is the limit as x goes to negative infinity of 5 over 3x. And that's going to be 5 over a really enormous number, which is 0 when we're done. C, lim as x goes to infinity of e to the negative x plus 2. If we go e to the negative infinity, that becomes a 0. And the 2 becomes a 2. Okay. Since 2 doesn't have any x's on it, it's not affected by any of this. So that gives us a final answer of 2. Number 7, end behavior model. So you have y equals 2x squared minus 3x all over 5x plus 1. An end behavior model is just a really, really simple function that gives the far left and far right behavior of the graph. When we're dealing with rational functions, just like the shortcut up above, you can just take highest power of the top and divide it by highest power on the bottom. And that's going to give us y equals 2x over 5. That means if you go far left or far right, this basically looks like a line with a slope of 2/5. Not exactly, but very close. And that's a whole lot easier to graph than the big rational we started with. Okay, number 8. This is finding right and left behavior models more or less by inspection. So y equals e to the x plus x squared. Let's deal with, first of all, left model. And that means x goes to negative infinity. As x goes to negative infinity, e to the x becomes 0. And x squared becomes really big. So clearly, to the far left, the thing that's making a bigger difference to the look of the function is the x squared. So that will be our left model. To the right means x is going to infinity. So again, we have this function. As x goes to infinity, well, x squared gets really big. But e to the x squared, so even if we compared these at a million squared compared to e to the million, e to the million is going to be way bigger. This is huge. Okay, and you can tell because my voice cracked on it. So it must be unbelievably big. So the e to the x is making a big difference. Let's do the same for b. We've got y equals sine x plus x squared. So left, as x goes to negative infinity, y equals sine x plus x squared. All right, sine x does not converge on anything, but it's oscillating between -1 and 1. X squared becomes really big. Okay, so we don't exactly know what sine x is doing, but in comparison, the x squared is way more important. And it turns out this one is basically going to look like kind of a jiggly parabola. The thing that really determines its shape is the y equals x squared, especially to the far left and far right. So far right is going to be the same here. Sine x plus x squared. The sine x is going to be between -1 and 1, and this is going to be really big. Therefore, y equals x squared is the end behavior model to the right as well. Okay, number 9, we're going to find and classify discontinuities. So A, we've got y equals 1 over x minus 2. Right away, we know that this looks like a butterfly or your basic reciprocal graph. That means that x equals 2, there's a discontinuity, and the type is an infinite discontinuity. Okay, those are what vertical asymptotes give us, are infinite discontinuities. B, y equals x squared plus 3. Now let's think, is there any number you can put into this that makes you do something illegal, like divide by 0 or square root of a negative or log 0 or negative. There's nothing. This one's fine. If I put in negative a million, no problem. If I put in 0, no problem. If I put in a million, no problem. So there are no discontinuities. C, we've got x squared minus 1 all over x squared plus 4x plus 3. We know by now we're going to need to factor that. That'll give us x plus 1 by x plus 3. Okay? And these ones that divide out, those are points of discontinuity. So at x equals negative 1, you have a point of discontinuity. And we call that a removable discontinuity. You could fix it by filling in that hole. Over here, this is a vertical asymptote. So at x equals negative 3, we've got an infinite discontinuity. Number 10, this is basically doing stuff from chapter 9 in the last course. So we have in A, y equals 3x squared plus 2 all over x squared minus 1. Horizontal asymptotes, if the powers are the same on top and bottom, then it's just highest power of the top divided by highest power of the bottom, which is going to give us y equals 3. Vertical asymptotes come from splitting this. So vertical asymptotes on this one would be at x equals negative 1 and x equals 1. And I need to see them written as y equals and x equals. You can't say horizontal equals or vertical equals. B, same idea. 3x squared plus x minus 2. Okay. Highest power is on the bottom, therefore the horizontal asymptote is y equals 0. It's the x-axis. Okay. If I want to figure out what the vertical asymptotes are, I need to factor this. So the bottom's going to factor into x plus 1 and minus 2/3. Or minus 2, rather. 3x minus 2. Okay. This one right here gives a vertical asymptote of x equals negative 1. And this one right here, the number that would cause that to be 0 would be positive 2/3. And you could work that out by saying, okay, what's going to make it 0? Oh, yeah. It's 2/3. Okay. So that'll be our other vertical asymptote. Number 11, we're looking for extended functions. So essentially, we want to remove any removable discontinuities. 11a is y equals x squared plus 3x plus 2 all over x plus 2. You likely want to factor the top and bottom here. And this is telling you that this function reduces down to x plus 1 as long as x is not equal to negative 2. And that there's a point of discontinuity at negative 2, and throw in that negative 2 into the simplified function, and you get negative 1. The easiest extended function you could write for this is y equals x plus 1, no restrictions. Okay. You could do another more complicated piecewise one that's also in your solutions. Y equals x minus 9 over root x minus 3. This one we're only looking to make it continuous over the set of non-negative reals. Okay, because obviously it's not going to exist when you put in negative x values. But this one does have a discontinuity in it. You can't put in the number 9 or else you're in trouble. So how do we deal with ones with radicals? We look at the conjugate. Or some people might have factored the top as difference of squares. You can do that too. This is the way we see more often. So root x plus 3 is going on the top. X minus 9 is going to show up on the bottom. Poof. So there was a point of discontinuity at 9 on this one. This function reduces down to root x plus 3 as long as x is not equal to 9. Well, the extended version would take out that restriction. It's just root x plus 3. Okay. Up here we should have said as well that this is the extended version. Okay. And again, there's a piecewise version in your solutions. Lastly, we have y equals sine 3x over x, which is defined almost everywhere except where x is equal to 0. So, I wonder what's going on around 0. Let's find the limit around 0. Figure out what its behavior should be. Okay, that's close to something we know about, but we really would like a 3x on the bottom, which means timesing by 3 over 3. That's going to give us lim as x goes to 0 of 3 sine 3x over 3, which is the number 1 when we're done with it, using our limit rules. So this will be 3 times 1, or 3. Okay, now that is not the equation of the extended function, but that will help us. So almost everywhere, this function is defined by sine 3x over x. The only place it can't do that is when x is 0. When x does equal 0, now we know this function should take on a value of 3. So there's the extended function that removes that discontinuity. Number 12. Consider f of x is 2x squared plus 1. Okay, so it's a parabola. It opens up. It's kind of steep. We want to find the slope of the secant from x is 2 to x equals 5. So if you want to find slope, it's no problem. It's just rise over run. Or if you know 2 points, then you can use slope as change in y over change in x. So let's find these 2 points. Somewhere out here, there's the point 2. And if I put 2 into the function, I'll get 9. Somewhere over here, there's the point 5. If I put 5 into that function, I'll get 51. Okay? And we're looking for the slope of this line. M is y2 minus y1 all over x2 minus x1, which would be 51 minus 9 over 5 minus 2, 42 over 3, or a slope of 14. B asks us for something a little bit different. It asks us, what is the slope of the tangent right here at 2? And it looks like it should be a little less steep. And if we want to find that tangent at 2, we need to know 2 things. F at 2, which is 9, and f at 2 plus h, okay, which is going to be 2 by 2 plus h all squared plus 1, or 2 by 4 plus 4h plus h squared plus 1, or 8 plus 8h plus 2h squared plus 1, or 9 plus 8h plus 2h squared. Okay, and we do all that so that we can use this. Slope of the tangent is equal to lim as h goes to 0 So 2 points that are infinitely close together of f at 2 plus h minus f at 2 all over h. Now that we've found each of those values, we can just follow the algebra through. So f at 2 plus h was 9 plus 8h plus 2h squared. F at 2 was 9. Okay, all over h. I'm just going to take h out as a common factor. You could take 2h, doesn't matter. Sorry, not 8h. But 8 plus 2h. Okay, the h's are gone now. So that gives us lim as h goes to 0 of 8 plus 2h, which of course is 8. And that is the slope of the tangent at x equals 2. We're doing the same sort of thing. We need to find the equation of the tangent at x equals 1. So to find the equation of a line, we need to know the point, and we need to know the slope. Okay. We want equation of tangent at x equals 1. So point is not hard. That's talking about a x value of 1. Put in 1, and we get, into this equation, we get 1 over 3. Okay? Slope. Use limits. Yay. Okay, and to use those limits, we need to know f at 1, which would be 1 over 3. And we need to know f at 1 plus h, which would be 1 plus h plus 2 on the bottom, or 1 over 3 plus h. Okay. Now we're ready to find the slope of the tangent. It's going to be lim as h goes to 0 of f at 1 plus h minus f at 1 all over h. So we'll stick with green. Okay, f at 1 plus h is 1 over 3 plus h minus 1 over 3 all over h. Nested fractions. Same tricks come back again and again. So that'll be the limit as h goes to 0 of 3 minus 3 minus h all over h by 3 plus h. Sometimes people forget to do the bottom part, so be careful of that. Okay, that gives us negative h over h, 3 by 3 plus h. These are gone. Gives us negative 1 up top. And as h goes to 0, the slope of the tangent is going to be negative 1 over 3 times 3 plus 0, or 9. Okay, that gives us the tangent. Now the last thing we need is the actual equation. And that comes from point-slope formula. And this needs to be memorized. Y minus y1 equals m by x minus x1. We said that y1, the point, right up here, the y value is a third. So y minus a third. The slope is right here. That's negative 1/9 by x, and x1 was the number 1. Okay, negative 1/9 x plus 1/9. Move that 1/3 over, and we'll get plus 4/3. 4/9 rather. Pretty similar for number 14. We want the equation of the normal in this one. So there's just going to be one extra little step. 2y equals root x minus 3 at x equals 5. And if you want, you can imagine what that looks like. Root x minus 3 is this shape. Okay. Its tangent would look like this, but its normal should look like this. Fairly steep, but negative. Let's see if that's what we get. Again, we need point and slope. So the point that we're going to do is 5, and put 5 in, you get root 2 for y. Slope, use limits, and you have to find the slope of the tangent first. Okay, so we need to find, let's assume that we were working in f's here instead of just y equals. So you'll have to find f at 2, f at 5 rather. Which will give us root 2. And f at 5 plus h, which would give us root of 2 plus h. Now we're going to find the slope of the tangent. Lim as h goes to 0 of f at 5 plus h minus f at 5 all over h. Plug in what we know. So that's going to be lim as h goes to 0 of root 2 plus h minus root 2. Okay, square roots. The way that we deal with this is through conjugates. Okay, work them out. That's going to be 2 plus h minus 2 up top. And on the bottom, it's going to be h by root 2 plus h plus root 2. Following along, that gives us h up top. And this is where the magic happens. You can finally divide out your h's. Because the problem was that we couldn't substitute. There was an h on the bottom. Lim as h goes to 0 of 1 over root 2 plus h plus root 2. As h goes to 0, that's just going to be root 2 plus root 2 on the bottom. Or 1 over 2 root 2's. Okay, so that was somewhat unpleasant, but not super tricky. That's the slope of the tangent. The slope of the normal is the negative reciprocal. So it's going to be negative 2 root 2 over 1, or negative 2 root 2. Okay, lastly, we want the actual equation. So the equation comes from point slope formula, which is again y minus y1 equals mx minus x1. y1, go up to the top. We'll see that it was root 2. M is negative 2 root 2 by x minus 5 was our x value. That'll give me negative 2 root 2 x, negative, fairly steep slope, just like we expected, plus 10 root 2. And if I add root 2 onto each side, here it is in y equals form. All right, lastly, number 16. The distance fallen in meters by an object in free fall in Kepler 186f is given by d equals 4t squared. Now we're just making up these values. We don't actually know what gravity's like on Kepler 186f, but it is a planet that's close to the size of Earth. Okay, find the average speed over the first 4 seconds. So if I were to graph this, the distance in free fall looks kind of like this. It's going to be measured in meters, so distance in meters, and time in seconds. There are two ways that you can approach A. So average speed is change in distance over change in time. Okay. When we get to 4 seconds, that'll be 4 times 4 squared, we'll be at 64 meters. So the change in distance will be 64 meters, and the change in time will be 4 seconds, or 16 meters per second. Or you could have done it as slope of a secant. That's what average rate of change is. Okay, so we're talking about the 0.00 and the 0.464. y2 minus y1 over x2 minus x1, 64 minus 0, all over 4 minus 0 is again going to give us 16. And we have to know that that's in meters per second. B talks about the instantaneous speed. So instantaneous, as soon as you see that, you should be thinking, oh, slope of the tangent. Exactly how fast is it going at this point? And it should be faster than what the average speed was, because you can see that the slope is steeper. Okay, to do this, we need to find d at 4, which would be 64, and d at 4 plus h, which would be 4 by 4 plus h all squared, or 4 by 16 plus 8h plus h squared, or 64 plus 32h plus 4h squared. All right, let's just find the slope of that tangent then. So it'll be d at 4 plus h minus d at 4 all over h. Working it through, that's 64 plus 32h plus 4h squared minus 64 all over h. Okay, 64s are going to be gone. So we're looking at the limit as h goes to 0 of 32h plus 4h squared all over h, or limit as h goes to 0 of, I'm just going to take h out as a common factor, that we could have taken 4h. And that's because I want my h's to divide. Limit as h goes to 0 of 32 plus 4h. Hey, now we can finally put in a 0 for h, and that'll give us 32, and the units are in meters per second, because we're still talking about slope, y's over x's. Okay, I hope you found this at least somewhat helpful. If there are any corrections, feel free to post them in the comment section below. And I will likely see you tomorrow.